Section 11.4, the comparison tests. Now there are two comparison tests that we're going to talk about in this section. The first one, which is called the comparison test, I like to also call it the direct comparison test. The second one, called the limit comparison test, so that we can distinguish between the two. But the idea behind both of these, obviously, is to make a comparison. And what we're looking at doing is comparing our series, the one that we're trying to determine the convergence or divergence of, to a known series. All right, and it has to be a series that we know either converges or diverges. And then we can use what we know about that series to help us determine convergence or divergence of our series. All right, so we're comparing a given series to a series that we know to be convergent or divergent. So for example, the first one, looking at the sum as n goes from 1 to infinity of 1 over 5 to the n plus 1, and comparing that to the series sum as n goes from 1 to infinity of 1 over 5 to the n. And it says, since 1 over 5 to the n is a geometric series, I'm like, well, wait, how do I know that 1 over 5 to the n is a geometric series? All right, so let's maybe step over to the side for a second. If you look at 1 over 5 to the n, remember our series, our geometric series and what those guys look like? If I look at the sum of 1 over 5 to the n, all right, our geometric series looks like this. This is our generic form, that AR to the n minus 1. And so I'm looking at recognizing a series that takes on that format. Well, see if you agree with this. I can take 1 and express that as 1 to the nth power. All right, as n goes from 1 to infinity, that's going to give me 1, right? 1 to the n. I could then take that and write it as 1/5 to the nth power, right? Using our properties of exponents. Excuse me. But now I can recognize that, look, the terms of that series, each successive term is the previous term multiplied by 1/5. All right, so my first term, when n equals 1, it's 1/5. The second term is 1/5 squared. The third term is 1/5 cubed, etc., etc. Right, so, even though in our kind of generic little form of the geometric series, we see this r to the n minus 1, remember that's all arbitrary notation. It's just a constant raised to a power, right? And so that each term of the series is the previous term multiplied by whatever that r value is, that constant, right? And so in this particular series, r is 1/5, but also notice a is 1/5. Remember, a is the first term of the series. And so when n equals 1, I get 1/5. There's my a. That's our first term. And then each successive term is the previous multiplied by 1/5. So that's how you can kind of recognize a geometric series. Look for things like this, where you see a constant raised to the nth power like this. Okay, that's an indication that you are looking at a geometric series, or at least a pretty good chance that you are. And so kind of recognize that. All right, so back to our series then. All right. So if we compare this series 1 over 5 to the n plus 1 to that series 1 over 5 to the n, knowing that 1 over 5 to the n is a geometric series that converges because r is 1/5. Remember, for geometric series, they converge if r is between -1 and 1, or if the absolute value of r is less than 1, which is true in this case. So we know that then that series is convergent. We also know it converges to a over 1 minus r, right, which is 1/5 over 1 minus 1/5, which will give us 1/4. That'd be 1/5 over 4/5. 1/5 times 5/4, I get 1/4. So I can actually know the sum of that series because it's geometric. And we said the geometric series are one of the types that we can actually calculate the sum. But again, I don't care about the sum of my series per se. All I'm interested in is the series convergent. Now, comparing our series to that series. So 1 over 5 to the n plus 1, we know is smaller than 1 over 5 to the n. And that goes back to what we've said many times. If I take a fraction and increase the denominator, it's going to decrease the value of the fraction. Right? Remember, there's that inverse relationship. So 1 over 5 to the n plus 1 is always going to be less than 1 over 5 to the n for all values of n. So if I look at the sum of 1 over 5 to the n plus 1, the partial sums for that series would always have to be smaller than the partial sums for that sum as n goes from 1 to infinity of 1 over 5 to the n, that geometric series. And that's simply because each of the terms of our series are smaller than the terms of that series. So if we add those terms together, my partial sums will always be smaller than the sums or partial sums of that geometric series. Right? So this means that for the sum of 1 over 5 to the n plus 1, the partial sums, now, just bringing in some of the things we talked about, the partial sums are increasing, right? We know they're getting larger if we keep adding stuff to them. We also know that those partial sums are bounded. We just said that the partial sums of our series would always be smaller than the partial sums of 1 over 5 to the n. We know the sum of 1 over 5 to the n is 1/4. We found that up here. So that means our series, the partial sums, are increasing and bounded. And that goes to that monotonic sequence theorem that we mentioned back in the first section that said that every monotonic bounded sequence is convergent. Monotonic meaning it's either increasing or decreasing. So if I have an increasing sequence that's bounded above, in this case it's bounded by 1/4, then I know that my series has to be convergent. All right. We also know that the sum of our series is less than 1/4. Right. Now again, remember, since I'm comparing it to that series 1 over 5 to the n, 1/4 is the sum of the series 1 over 5 to the n. We know that the sum of our series is smaller than that. Right? So I still don't know what the sum of my series is, but at least I know it's less than 1/4. Now again, all we're going to be interested in is determining convergence or divergence. We're not going to be interested in determining the sum or finding the sum unless we can, in certain cases, like a geometric series, we can find the sum. Right. But in general, and notice there is a limitation on the use of these comparison tests in that the terms of the series have to be positive terms. So if we have negative terms involved, this test does not necessarily apply. And the observation is similar to what we talked about with that integral test in the last section. I want to compare my series to a convergent series if I know that the terms of my series are smaller than those terms of the convergent series. I want to compare my series to a divergent series if I know that the terms of my series are larger than those of a divergent series. And it's a similar discussion that we had in that previous section. My series is convergent if the terms of my series are always smaller than those of a convergent series, right? So smaller than a convergent series means it has to converge. I know that my series will diverge if the terms of my series are always larger than those of a divergent series. Right? So larger than a divergent series would also have to diverge. So when you're using comparison tests, there's actually two kind of parts to that, or two things that you have to be careful of. First of all, you have to recognize which series you're going to compare it to. Have to compare it to something that I know, or a series that I know something about that either converges or diverges. Secondly, you have to have the right comparison, right? In order to use this, what we're calling, I'm going to write up here, direct comparison test. Right? So it's just called the comparison test. I like to call it the direct comparison test so that when we talk about the other one, I don't confuse the two. So this is direct comparison. So I need to show that my series is either smaller than a convergent series or larger than a divergent series. And that's what the direct comparison test tells us. So suppose that I have a sum of a sub n and b sub n that are series with positive terms. Remember that restriction. If the sum of b sub n is convergent and a sub n is less than or equal to b sub n for all values of n, then the sum of a sub n also has to converge. Right? So that's just saying, again, if I could show that my series is smaller than a convergent series, then my series has to converge. The second part of that, if that sum of b sub n, that series is divergent, and the terms of my series, a sub n, are always larger than those of b sub n for all n, then a sub n also has to be divergent. Right? Larger than a divergent series has to diverge. Now, comparing it to known series, right, then we don't have a whole lot to work with just yet. We've only talked about a couple of types of series. So known series that we use for these comparison tests, first of all, the p series, we talked about that sum of 1 over n to the p. When we showed that that was convergent if p was greater than 1, and it was divergent if p is less than or equal to 1. So our p series. We also have our geometric series, right? So like in the example we just had, that sum of a times r to the n minus 1, or again recognizing a series of the form where I'm multiplying each term by a constant to get the next term. So you see r to a power, a constant to an nth power, or n minus 1 power. We know that that series, or the geometric series, is convergent if the absolute value of r is less than 1. I said if the r value is between -1 and 1. And it's divergent if the absolute value of r is greater than 1. Now the third series, and really it's not a separate type of series. We do mention it as a third series because we see it pop up so much. We talked about that harmonic series, the sum of 1 over n. But again, the harmonic series is really nothing more than a p series. It's a p series with p equal 1. Right? It's 1 over n to the first. So yeah, it's a special series just simply because we see it used quite often. But it is nothing more than a p series. Right? So we have p series, we have geometric series that we can compare our series to. So next example. Let's say it wants to jump like that. So I've got the sum. In this case, as n goes from 2 to infinity. And this is something that we mentioned before. I don't think we've had an example with one. But here I'm starting at n equals 2 because notice if we started n equals 1 for our series n cubed over n to the fourth minus 1, the first term would be undefined, right? But n equals 1. So, as we said when we were talking about these indexes, or the n values, it doesn't matter really where you start. Because we are looking at an infinite number of terms as n approaches infinity, the first 1 or 2 or 5 or 10 or 1,000 or 1,000,000 terms really doesn't matter. It's what happens as we approach infinity. All right, so this sum as n goes from 2 to infinity of n cubed over n to the fourth minus 1. And the trick with this comparison test, or these comparison tests, is going to, like we said, you have to recognize which series or what type of series you're going to compare it to. And part of that's going to require some rewriting on your part. It's similar to like what we had to do with integrals. We were trying to integrate, and maybe we had to manipulate the integrand to fit a certain format. Or when you're using finding derivatives, right, and you want to use a particular rule for differentiation, and you would maybe have to rewrite or manipulate the function to put it into a form that you could use, say power rule or product rule or what have you. There's a lot of rewriting involved with our series in order to use comparison tests because you have to be able to make a clear comparison between your series and the series that you are comparing it to. So taking, for example, in this case, dividing the terms of our series by n cubed. Why divide by n cubed? Because that then gives me the form of the series as 1 over n minus 1 over n cubed if we divide everything by n cubed. And that would allow us then to compare our series to this, 1 over n, right? So our harmonic series. So that's going to be part of the trick with these, and that's really, I guess it's probably the trickiest part in that, okay, how do I manipulate my series so that I can put it into a form to where when I pick a series to compare it to, the comparison between those is obvious. I mean, because there's no guess, there cannot be any guesswork here. It can't be, it says, I can't just say, oh, it looks like this is less than or greater than this series. I have to be able to say without a doubt that it is for all values of n. Right? So like in this case, comparing to the sum of 1 over n, if I look at 1 over n minus 1 over n cubed, okay, this is our series, and I compare it to this harmonic series 1 over n, I know that the terms of our series are always going to be larger than that, because what's the comparison? Well, we change the denominator. Our denominator is smaller than that of 1 over n. But if we decrease the denominator, what happens to the size of the fraction? The fraction gets larger. So our terms are always going to be larger than that of 1 over n for all n values greater than or equal to 2. And since our series 1 over n is divergent, that's our harmonic series, then our series must also diverge, because the terms of our series are always larger than the terms of that harmonic series. So therefore, the sum as n goes from 2 to infinity of n cubed over n to the fourth minus 1, which is our original series, is a divergent series by the comparison test. Now also notice here what I'm doing. I'm telling you how I made my determination. When you are determining convergence and divergence of a series, it's not sufficient just to say, oh, hey, it's convergent, or it's divergent, or it looks like it's convergent, or maybe it looks like it's divergent. No, you have to have some reasoning behind it, right? Because, I mean, otherwise it's a 50-50 proposition. It's like, okay, maybe it's convergent. It looks that way. Or I think it's divergent. You have to give a reason. You have to show. You have to prove, right? So to say that it's convergent or to say that it's divergent, how did you make that determination? What test did you use? Okay. So, and also too, when you make your final statement, you know, if you want to rewrite the entire original series, fine. Or if you just want to simply say that the sum of a sub n, and I'll take that to be the original series, you know, so if, because some of these are going to get a little funky looking, they're going to be a little intricate. And so if you don't want to have to rewrite all of this, just give me a generic a sub n, and that's fine. But you do have to give a final statement. You do have to give a summary statement in that the sum of our series is either convergent or divergent by what test, right? So by the comparison test, or with some of the other tests that we're going to look at, okay? All right, so that's the comparison test, or again, what I was calling the direct comparison test. The other comparison test is the limit comparison test, right? Now, initially it's the same idea. I want to compare our series to a known series that converges or diverges, but the comparison here has to be a little different, and I'll give you an example as far as why. And how do I recognize, okay, when do I use which one, or do I have a choice? So let's suppose, again, we have two series, a sub n and b sub n, that are series with positive terms. So just like the direct comparison test, this limit comparison test requires that the terms of the series are positive. If the limit as n approaches infinity of their ratio of a sub n to b sub n is equal to some c value, where c is a finite number and it's positive. Let's keep hitting the wrong thing up here. So I'm looking at the ratio of the terms of our series to those of a known series. And if that limit, or the limit of their ratios, is equal to a positive constant, then the limit comparison test says that either both series converge or both series diverge. So in other words, they either both have to be convergent or both divergent if this limit is a positive constant. And I kind of think of it this way. If you have the terms of your series a sub n, the terms of your known series b sub n, if the ratio of those terms is always the same, it's always a constant value, then I think of it as the two series having terms that are kind of increasing or decreasing in conjunction with each other. In other words, for this ratio to remain the same, in order to get the same c value every time when you look at the ratio of a to n over b sub n, then the rate at which those two terms is increasing or decreasing has to be constant. And so whatever b sub n is doing, a sub n would have to do the same thing in order for that ratio to remain constant. And then, as usual with this, I mean, if you want a more in-depth discussion or explanation as far as why this limit comparison test works, then you can look at this section and read the textbook. But that's the basic gist of it. Right? Bottom line is, though, if I look at the limit of the ratio of our terms of our series compared to the terms of a known series. If I get a positive constant when I evaluate that limit, then either both series converge or both series diverge. And that's again why you have to know convergence or divergence of the series you're comparing it to. It doesn't do me any good to compare it to a series that I don't know whether it converges or diverges. Right? So for example, I've got in this case the series sum as n goes from 1 to infinity of 1 over 2 to the n minus 1. In this case, I'm going to compare the series to 1 over 2 to the n. Here I'm using limit comparison test. Let me ask this first. Why can't I use direct comparison here? Or, well, maybe could I use direct comparison here? So first of all, recognize I'm comparing it to 1 over 2 to the n. What type of series is that? And that is a geometric series. Right? Remember we said when I'm looking at those constants raised to a power, get this thing working. Right. So remember 1 over 2 to the n, 1 over n, or 1/2 to the n. All right. So the sum of 1 over 2 to the n is a geometric series with r equal to 1/2. So what does that mean? Well, that means it's a convergent geometric series, right? But notice the terms of our series. Now, our series in this case was 1 over 2 to the n minus 1. Now, if you compare 1 over 2 to the n minus 1 to 1 over 2 to the n, what's the comparison there? Well, we decreased the denominator over here, which means we made the fraction larger, right? So if I take 2 to the n and subtract 1 in that denominator, the fraction gets larger. So then the comparison here, in terms of a direct comparison, our series is larger than a convergent series, okay? And remember, that doesn't do me any good. You know, if my terms of my series is greater than that of greater than a convergent series, that doesn't tell me a thing. My series could converge. It might diverge. I don't know. Right? So that's why we said you have to be able not only to recognize first what series to compare it to, but you also have to have the proper comparison to use these tests. And so this is kind of how you can recognize, you know, when can I use comparison tests versus using limit comparison tests. Right? And I always start out checking first direct comparison. If what series can I compare it to, P series or geometric series. And if my series is greater than a divergent or less than a convergent, then I'm good. I'm done. But if we have something like in this case, my terms are larger than those of a convergent series, direct comparison doesn't work. So then the next best option is this limit comparison test. Right? So that's what we're doing in this case. So that's kind of your telltale. You know, how do I determine which limit or which comparison test to use? Try direct comparison first. If it doesn't work, if I don't have the right comparison between my series and the known series, try limit comparison test. All right, so we're going to let a sub n be the term, be our series, 1 over 2 to the n minus 1. We'll let b sub n be our comparison series, 1 over 2 to the n, convergent geometric series. We look at the limit of their ratios. Limit as n approaches infinity of a sub n over b sub n, which would be equal to the limit as n approaches infinity. Limit statement of 1 over 2 to the n minus 1 over 1 over 2 to the n, which would be the limit as n approaches infinity of, multiplied by the reciprocal, 2 to the n over 2 to the n minus 1. And in this case, I'm going to divide everything by 2 to the n. Right? So like we've done before with those rational functions and dividing by n to whatever power, In this case, I'm dividing by 2 to the n. Why? Because it puts it into a form that I can evaluate the limit. Right? It's all about evaluating the limit. Once you write this limit out, it's all about evaluating the limit, whatever it takes to do that. So dividing everything by 2 to the n gives me 1 over 1 minus 1 over 2 to the n. And as n approaches infinity, right, this would approach infinity, so this would approach 0, and we're left with 1. Now for this limit comparison test, what does it say? If that ratio is a positive constant, right? So be careful, because we're going to talk about some other tests going forward, and not just be, applying the test, but interpreting the results. And so for limit comparison test, what do I want to see? In order to be able to use it, I need the ratio of my series to my comparison series to be equal to a positive constant, any positive constant. And then what does that tell me? If that happens, then I know that either both series are convergent or both series are divergent. And since I compared my series to this convergent geometric series, then my series also has to converge. So since the series that I compared it to is convergent, then my series is also convergent by the limit comparison test. Don't worry about that. That's an old note. Okay. All right, I'm going to do some other examples. That's it for the formal notes in this section, but I do want to do a couple of other examples, because I know these. I said it's pretty straightforward if you have the right comparison. If you recognize what to compare it to, comparison test is pretty straightforward. Right? But that's the trick. That's the problem. You have to recognize what to compare it to, and then do I have the right comparison? So let's take this one for example. I've got the sum is equals from 1 to infinity of 6 to the n over 5 to the n minus 1. Right? My comparison in this case, do you recognize, or can you recognize what series I would compare it to? Well, there's that, 6 to the n, 5 to the n. What do we say that I should recognize that as what type of series? That's a geometric series. I'm going to compare 6 to the n over 5 to the n minus 1 to 6 to the n over 5 to the n. Recognize that that's a geometric series. Right? I could write that as 6/5 to the n. Yeah. So there's a geometric series with r equal to 6/5, which is greater than 1, which is a divergent geometric series. But here's the comparison. First of all, I'm recognizing that I'm going to compare it to this divergent geometric series. So I need the comparison to be greater than, right? I need my terms to be larger than those of that geometric series. And that's what we have in this case, because if I take that denominator and decrease the denominator by 1, I'm increasing the size of the fraction, right? So our series, our terms, are larger than those of that geometric series. Right, now that's just the comparison. So what can I then say? I can then say that the sum then goes from 1 to infinity of our series 6 to the n over 5 to the n minus 1 is greater than the sum then goes from 1 to infinity of 6 to the n over 5 to the n, which is a divergent geometric series. Right. And it's geometric in this case, or divergent, because r is 6/5, right, which is greater than 1. Remember, r greater than or equal to 1 is divergent. R less than or equal to 1, or we'll say between -1 and 1, or the absolute value of r less than 1, is convergent for those geometric. And so since our series is greater than a convergent series, therefore the sum as n goes from 1 to infinity of 6 to the n over 5 to the n minus 1 is divergent by the comparison test, right? The direct comparison test, more specifically. But we just call it the comparison test. Okay. Here's another one, a little more interesting maybe. I know y'all love your trig functions. I got the sum as n goes, or k in this case, goes from 1 to infinity of k sine squared k over 1 plus k cubed. I know as soon as we see a trig function, we panic. Oh, what am I going to do with that? Well, you have to, again, rely upon things that we know. That's the trick with these. With a lot of this stuff we talk about, you have some pre-existing knowledge that you have to rely upon. Recall, dangerous word, right? What do you know about the values of your sine function? I know that the values of sine always fall between -1 and 1. That's the range of the sine function. So in other words, the absolute value of the sine of k is always less than or equal to 1. Right? Sine is always between -1 and 1. So if I square that, I'm still going to get values that are less than or equal to 1. So that's going to be that's kind of the trick with this one, is recognizing that, hey, the terms of sine squared k for all values of k would have to be less than or equal to 1. So what does that then mean for my series? Well, since sine squared k is less than or equal to 1, then k times sine squared k over 1 plus k cubed, or maybe k over 1 plus k cubed times sine squared k, would have to be less than or equal to k over 1 plus k cubed. Let me write it this way. We know that this has to be less than or equal to k over 1 plus k cubed, right? Because this is less than or equal to 1 times k over 1 plus k cubed is going to give me something smaller than that. So that's kind of the important recognition with this one, right? But keep that in mind with your trig functions, sine and cosine especially, right? The values of those functions, the range, -1 to 1. Now, k over 1 plus k cubed, we can work with that like we've done before. If I divide everything by k, then I get 1 over what? 1 over k plus k squared. So that's rewriting k over 1 plus k cubed, dividing everything by k. So that now I can actually compare this series to what series? 1 over k squared. Now what's the comparison between this series and 1 over k squared? Well, 1 over k squared, we're adding 1 over k to that denominator. If we add or increase the denominator, what happens to the fraction? The fraction gets smaller. So this, we know, is less than 1 over k squared. Now, what do you know about 1 over k squared? If I put that in terms of a series, what type of series is that? That is a p series. That's our 1 over n to the p, or in this case, 1 over k to the power. It's a p series with p equals 2. What do we know about convergence and divergence with p series? P series converge if that exponent is greater than 1. And they diverge if the exponent is less than or equal to 1. So now notice the progression here from left to right. our series, the original, is less than or equal to k over 1 plus k cubed because of what we know about the sine function values, which is equal to 1 over 1 over k plus k squared. That's just a rewriting of that function, which we know is less than 1 over k squared. So ultimately then we can say that the terms of our series would have to be less than the terms of these guys, because that is less than that, which is equal to that, which is less than that. So progressing from left to right, our series is always going to be smaller than 1 over k squared. So the sum, as k goes from 1 to infinity, of k sine squared k over 1 plus k cubed would be less than the sum, as k goes from 1 to infinity, of 1 over k squared. Okay? But that's what we said before in terms of being able to rewrite, being able to manipulate, so that I have a clear comparison between my series and a known series. Right, so we just said we know that 1 over k squared is a convergent p-series, and why is it convergent? It's convergent because our p-value, which is 2, is greater than 1. And p-series converge for values of p that are greater than 1. So therefore, now I'm not done, I still have to make my final statement. So our series is smaller than that convergent p-series. Therefore, the sum as n goes from 1 to infinity of our series, and again, if you just want to write a sub n here, you don't have to rewrite the entire series. I'll take that. We know that this series has to be convergent because it's smaller. Because it's smaller than a convergent p-series. Okay. All right, I have one other example. I want to give you another example with that limit comparison test. All right, for this one, we got the sum as n goes from 1 to infinity of 2 over the square root of n plus 2. Now, I think the comparison by now should be a little bit obvious, a little bit more obvious, in terms of the type of series or the series I may want to compare this to. So how about we take 2 over the square root of n plus 2. Now, what would you compare that to? Well, let me ask, I guess, first, what type of series would you compare it to? Well, I'm looking at my n, square root of n, or what, n to the 1/2. So maybe comparing this to a p-series with p equal to 1/2. So how about I compare that to, and maybe in this case, maybe not just 1 over square root of n, but how about 2 over square root of n? All right. If I compare those two series, which one's larger? The one on the right is larger because the one on the left has the larger denominator. Right, so we took square root of n, added 2, makes the denominator larger, which makes the fraction smaller. Right? So our series, the terms of our series, are smaller than 2 over the square root of n. Now, 2 over the square root of n, that's just 2 times 1 over the square root of n. Right? And this is the one I'm interested in, because that now I can tell you is what, convergent or divergent. It's a p-series with p equal to 1/2, less than 1, divergent p-series. But that presents a problem, right? Let me write that and then recognize the problem that we have. I'm going to say the sum of 1 over the square root of n is a divergent p-series because p in this case is 1/2, which is less than 1. Right? We said less than or equal to 1, p-series diverges. But that's the problem because our comparison over here was that the terms of our series are smaller than or less than the terms of 1 over the square root of n, or twice that. Smaller than a divergent? That doesn't tell me anything, right? So this is that case where, I recognize that maybe comparing it to this p-series is an appropriate comparison, but the direct comparison doesn't work, right? Because our series is smaller than a divergent series. So that's what leads us then to the limit comparison test, right? So direct comparison doesn't work. Let's try the limit comparison test. Now, what does the limit comparison test say? We're going to take a comparison between our series, which is what I'm going to call a sub n, 2 over the square root of n plus 2, and b sub n is the series that we're comparing it to, which is 1 over square root of n, right? That divergent p-series. And then we look at the limit as n approaches infinity of a sub n over b sub n. So 2 over that 2 over square root of n plus 2 over b sub n, which is 1 over square root of n, and multiply by the reciprocal. So I've got the limit as n approaches infinity of 2 square roots of n over square root of n plus 2 okay. And then to evaluate that limit, what would you do? Let's divide everything by square root of n. Notice in this case we're trying, as we always have with these rationals, and notice I'm not using L'Hopital's rule. I mean, you could, but I'm going about it by dividing by that highest degree of the variable in the denominator, like we've done before. Okay. But you're still just evaluating the limit. I mean, so if L'Hopital's rule applies, you can use L'Hopital's rule. And we still get the same conclusion if the limit is equal to a constant that's positive. Then either both series converge or both series diverge. So dividing everything by square root of n, that's why I'm going to do it. So that'll leave me with just 2 in the numerator. And then that would give us, 1 plus 2 over the square root of n in the denominator. And then as n approaches infinity, all right, this is going to approach 0, and I'm left with 2 over 1. And then my observation, okay, so that's the value of the limit, which is the limit of the ratio of my series to the b sub n, 1 over square root of n. And I get a value of 2, which is a positive constant. And since the value of the limit is a positive constant, then either both series converge or both series diverge. And since I compared that to a divergent p-series, then our series must also diverge. So since the sum as n goes from 1 to infinity of 1 over square root of n diverges, and then our series, the sum as n goes from 1 to infinity of 2 over square root of n plus 2 diverges. And in this case, by the limit comparison test. Okay? So I'll give you a few examples with those. And that'll be it for that section.